Hello everyone, and welcome to today's presentation on machine learning. I'm excited to have you here as we explore some important concepts. Today, we'll be focusing on overfitting, a key challenge in machine learning model. Our focus today is on a common challenge called overfitting. The title of our talk is, What is Overfitting? And we'll also look at why it matters and how to recognize it. Overfitting happens when a model learns the training data so well that it also captures noise and random fluctuations. This leads to a key issue. The model performs really well on the data it was trained on, but struggles with new, unseen data. Think of it like a student who memorizes answers instead of understanding the concepts, doing great on practice tests, but failing in the real exam with unfamiliar questions. Over the next slides, we'll dig deeper into how this happens and what we can do about it. Let's take a closer look at some common causes of overfitting. First, model complexity plays a big role. If the model is too complex, say it has too many features or a deep neural network with many layers and nodes, it can start to memorize the training data instead of learning general patterns. Next, insufficient data is another key factor. When the training dataset is too small or doesn't capture all the possible variations and patterns, the model can end up overfitting by trying to fit what little data it has too closely. Then there's noisy data. This includes errors, outliers, or irrelevant information within the dataset. The model can mistakenly interpret these as meaningful signals, leading to overfitting because it's trying to fit noise rather than true patterns. Finally, the amount of training time matters. Training a complex model for too long, like running too many epochs, can cause the model to become overly tailored to the training data, which reduces its ability to generalize well to new, unseen data. All of these factors contribute to overfitting, and understanding them helps us develop strategies to prevent it and build more robust models. Now, let's talk about some effective methods to prevent overfitting in our models. One key approach is cross-validation. Specifically, techniques like k-fold cross-validation are really useful because they help us get a more reliable estimate of how our model will perform on unseen data. Instead of just splitting our data once, we divide it into multiple parts, train on some, validate on others, and rotate through these folds. This process gives us a better sense of the model's robustness. Another important method is simply using more data. Increasing the size of our training dataset provides the model with more examples to learn from, which naturally helps prevent it from overfitting to a small, specific set of data. Additionally, data augmentation plays a crucial role, especially with tasks like image recognition. By rotating, flipping, or otherwise transforming existing images, we make our dataset appear more diverse. This diversity helps the model generalize better because it learns to recognize objects under different conditions, reducing the chances of overfitting. These strategies are all about giving our model the right amount of variety and validation to perform well on new, unseen data, which ties back to our overall goal of building robust, reliable models. Now, let's continue exploring methods to prevent overfitting. One effective approach is feature selection. This involves removing irrelevant or redundant input features that don't contribute much to the model's performance. By doing so, we help the model focus on what's truly important and reduce the risk of it fitting noise in the data. Next, we have reducing complexity. This means designing a simpler model architecture, such as using fewer layers or less depth in decision trees, often through a technique called pruning. Simplifying the model helps prevent it from capturing unnecessary details that don't generalize well to new data. Finally, early stopping is a powerful technique. It involves halting the training process as soon as we notice the performance on the validation set starts to decline, even if the training performance is still improving. This way, we stop before the model starts overfitting, ensuring it maintains good generalization ability. All these methods are about balancing the model's complexity and its ability to learn meaningful patterns, which ties back to our overall goal of creating robust, generalizable models. Now, let's look at some key methods we use to prevent overfitting. These are known as regularization techniques. Essentially, Regularization involves adding a penalty to our loss function that discourages overly complex models. By doing this, we help our models generalize better to new data. One common approach is L1 regularization, also called lasso. It penalizes the absolute value of the weights, which has the interesting effect of encouraging some weights to become exactly zero. This effectively performs feature selection, helping us identify the most important variables and simplify our model. Then there's L2 regularization, often called ridge or weight decay. This method penalizes the squared magnitude of the weights, pushing them towards zero, but rarely all the way there. It helps prevent any single weight from becoming too large, which can reduce overfitting without eliminating features entirely. For neural networks, we also have dropout. During training, dropout randomly ignores a fraction of neurons in each step. This forces the network to learn more robust features because it can't rely on any one neuron all the time. It's a powerful way to make the model less dependent on specific pathways and improve its ability to generalize. Overall, these regularization methods are crucial tools to keep our models from overfitting and help them perform better on unseen data, which ties directly into our goal of building reliable, generalizable models. Thank you for watching. Like, share, subscribe to EC Learning 360 YouTube channel.